Okay, so today we're going to start looking at module number 6. Module number 6 is force analysis on structures and machines. And most specifically, we're going to be looking at trusses, frames, and different types of simple machines. So if we look in our learning plan here, you're going to notice that we are going to be going away from the McGraw-Hill book again. I just am not really happy with how they did this unit either. And sometimes it just takes like getting your nose in there. So I am going, out of a handout this time. So this is a chapter 6 handout, not the McGraw-Hill. So all of the homework and all of the notes are coming out of this handout. Now, additionally, you'll notice that number 3 here says, download a free copy of MD Solids. At the beginning of our term, I had just said that we have this software. They weren't able to get it onto the computers here. There is a way that we can access it online or on the computers here, but the best way to do it is to download it on your own device, whether that's a computer or a laptop. Okay. So between today and the next time we meet, which is Thursday, I encourage you to get that free download available on a computer. I have the link to the website. On the left-hand side, there's going to be a place where it's a downloads tab or a page to click. Don't do it right now, please, because I don't want anybody messing around with it right now. It's not necessary this evening. But then you're going to notice that on that page, there's a free code. So when you go back in, you can download it. You'll go through the process. And the first time you go in, it's going to ask you for a username. You can just put your initials in or your name. And then it's going to ask you for a registration code. This is that registration code. And then it's going to be free. Okay. You don't have to pay anything for it and you have it indefinitely. What happened was the gentleman who developed this passed away some time ago. And since he's passed away, his family just offers it free. And as long as it runs on our Windows computers, we keep being able to use it. It's used out in industries. It's used at other universities. And it's a really nice resource that we're not only going to use in this class, this will be our first time to use it, but you're going to find it come in handy for subjects that are coming ahead in like strength of materials and in machine elements and things like that. So we'll be referencing it. So it's good to have a copy of your own because it's I don't know, it's really nice and easy, and you'll see that it's very useful. So not needed tonight. I'll demonstrate it tonight so you can kind of see what the environment looks like, but we'll have it by the next time that we have class. Okay. And then you'll notice that down here we have 2 guided notes. One is on trusses. That's what we're going to be going over tonight. And then the second one is on frames and machines. And that's what we're going to be looking at on Thursday. I divided it into 2 because we had that one that was like 22 pages long and it just felt so thick and just a lot. So I divided this into 2 sections. So there's 2 guided notes for this module. If you're in the room, they're up here in hard copy form. Otherwise, make sure that you're taking good notes, and including like the fill in the blanks and stuff like that we have, if you can't print it off. And then the practice problems that we're going to do are included in the guided notes, throughout those 2 handouts. So I just have those listed here that we'll be demonstrating in class. All of these page numbers correspond to the chapter 6 handout up here, not the McGraw-Hill book. Okay. So even your homework assignment is going to be out of this chapter. Okay. It's that same book that we used in module number 4, but it's just a different chapter. And then there's just going to be practice problems and application problems due for this, just like we normally would. As we go back a level, you'll notice that those are here. They're due March 1st at the end of this week, but as you know, you have your 7-day grace period. So that still is in play. Any questions module 6 wise so far? Okay. So then we're gonna look underneath our camera. Okay. So as we look here underneath our camera, this is the guided notes for our first section, which is going to be on trusses. But then this is the handout of the chapter that we're going to be referencing throughout. Okay, so I've got both of these underneath mine. If you wanted to pull up the PDF of the chapter handout, you certainly can do that to follow along. Otherwise, you can just kind of take notes here. So module 6 is about analysis of structures and machines. And most specifically, the structures we're talking about are going to be trusses and frames. Okay. So at the beginning here, it says a blank consists of a series of connected structural members or rigid bodies that are designed to blank loads and forces. So a truss and a frame consists of, so trusses, maybe trusses and frames consist of a series of connected structural members or rigid bodies. That means that they're not moving. Okay, they're static, they're not moving, and they're designed to support loads and forces. So they support loads and forces. Okay. Frames and trusses really do the same job in the end. They support loads and forces safely. Okay. The way that they do it is slightly different, but they really do the same type of end job. A machine, on the other hand, machines are designed to transmit loads and forces rather than to support them. So they're taking a load from one place and going to another. When we talk about simple machines, many times not only are they transmitting forces, but they're also able to give us a mechanical advantage. And you've probably seen this in physics with pulleys and levers and things like that. Okay, so we'll be looking at some pulleys, we'll be looking at some lever situations in the terms of like hand tools where we can get a mechanical advantage out of them, but we can show how the forces are transmitted, you know, through the different setups of the machines. So in this module, we're going to be specifically looking at trusses, frames, and machines. Okay, trusses, frames, and machines. The first part of our chapter is going to be looking specifically at trusses. Now, before we move to our first section, on page 101, which is the first page of this chapter, they're showing examples of each one of these. The first one they're showing us here is the truss. So a truss, familiar to us, is going to be something that is going to be connected many times, not always, but many times in a configuration where we start to see triangles form. Okay. And what we are going to be doing is analyzing each one of the members. And when we talk about members, it's going to be each one of these, portions in between what is also referred to as joints. On a truss, we are going to find that we can only put applied loads at the joints. We can't put them in the middle of a span. Once we do that, that becomes a frame. Okay, so a frame, as we can see here, it is also connected with pins, but we now can put our forces anywhere along the span as opposed to having them at the joint. Okay, then down below, the last two are different forms of different machines that we can encounter in this chapter and or out in industry. So the use of a pulley to gain mechanical advantage or to transmit a load. Or also we have here a crank mechanism. So we'll be looking at things like that throughout the chapter, starting first with analyzing trusses. And that's what we're going to focus on tonight. We've got two larger problems that we're going to be working through to get the idea of how to solve those types of things. Okay. So I'm going to go back underneath here. In section 6.2, we're talking specifically about simple plain trusses. So a truss, again, is going to be a structure usually consisting of straight uniform bars and members arranged in a series of adjoining triangles. Where do we see trusses? Where have you seen, things that look like that? Okay. What was that? Bridges. Yes, that's the obvious, right? Bridges can be, we see trusses. Where else do we see trusses? Drop ceilings. Oh yeah. In the inners of cardboard, they have like those little triangles. Yeah, those would be forms to kind of stiffen things up and take a load. Absolutely. Yeah. Anywhere else that you can think of? Houses, the roof lines, right? We're gonna see that those are trusses. And most specifically, the primary purpose of a truss is going to be two things: to distribute a load, and it's also going to be to span larger distances. So we've got to get over a river. right, with a road, a bridge is going to be the natural, and flanking it with trusses makes a lot of sense. Okay. Now, there are assumptions about simple plain trusses that we're going to make in our analysis. First of all, the bars are connected at their ends to form joints that behave like frictionless pins. Frictionless pins, where have we heard that before? Module 5, yeah, that was one of our supports, right? When there's a pin support, we have how many reactions? 2, right? An X and a Y. So we're going to see some of that play out here as well. Okay, so things are connected by frictionless pins. Number 2, all the forces acting on a truss have to be applied at the joints, as we had said earlier. Okay, we cannot have anything mid-span. It's going to be at those endpoints of where those members are connected. The members, joints, and loads lie in one plane. So we're not looking at something that has like a Z axis. We're only going to be looking in 2D, if you would, X and Y. Okay. And then we're always going to be under the condition of equilibrium. So we're assuming that our truss is supporting and it's not moving. So all of our forces, all of our moments are going to equal 0, are going to equal 0. Now, as we look down here, it says the analysis of a truss involves finding the magnitude of the force in each one of the members that are along the truss. Now, in addition to the magnitude of the force that's in the member, we need to also identify, is that member in tension or is it in compression? Okay, and we know that by looking at the direction of the force. If the direction of the force is pulling away from the joint, it is in tension. It's pulling on it. If the direction of the force is pushing on the joint, it is in compression. Okay, so we're going to know by that direction. And we know that as we work our equations of equilibrium, if we end up with a negative value, it tells us we're in the wrong direction. So we're going to be flipping some forces as we're moving around here to make sure we have them in the appropriate direction, but then also using that direction to identify, am I in tension or compression with this member? So as we look at a truss, this is a member between all of these joints. And we need to figure out what is the force in each one of those members and is it in tension or compression? Okay. Now, why would knowing if it's in tension or compression be important to me, do you think? I know we haven't really gone there yet, but it could be important later on. What would we want to be interested in knowing that for? Strength of materials, yes. And when we most specifically is what is the type of material that we're going to want to make this structure or this truss out of. Many times we see bridges made out of steel. Okay. And they're made out of steel because when I can have loads being in tension or compression, steel is one of the few materials that, for a couple different reasons, it's relatively inexpensive to make. It's actually quite inexpensive to make in comparison to others. But it also has this ability to reverse load in almost identically in compression as it does in tension, which is really cool about it. Many materials can do something more in one direction, but not in the other. For instance, cast iron. Cast iron is a material that can take compression all day long, but you start pulling on it, it's going to crumble and pull apart in no time. Steel, on the other hand, can reverse load and pull and push in both directions almost identically. Okay, that's why it is a very nice material to work with. It's very diverse, if you would. It can be used in a lot of different applications. Okay, so we see a lot of bridges made out of steel for exactly that reason, because we're going to see members in tension and in compression at the same time. Okay, so and then also knowing it's in tension or compression, we can then maybe even change out the materials in certain places to play to that specific direction. Okay, so let's get into how we're going to do this. So in section 6.4, this is called method of joints. And this is going to be the process that we're going to go through in solving these truss problems. Now, again, the end goal of a truss problem is to determine what is the force in each individual member that makes up this entire truss. And not only the magnitude of the force in that member, but is it in tension or compression? Okay, it's going to be one or the other. So each of your answers is going to either have tension or compression, and that's going to be based on the direction that it's moving or that's pointing in the free body diagram. So first things first, the process. Number one, we need to draw a free body diagram of the entire truss together, okay? So we don't want to forget our convention, but this is going to be so that we can determine in step number two, the reactions at the supports of that whole together truss. Okay, so we're going to see that there are supports, probably a pin and a roller, and we got to figure out, just like we did in module 5, what are the reactions at those supports. Then what we're going to do is we're going to break down into each one of the individual joints, and we're going to start at a joint where we seem to know the most. Now, that might not make a lot of sense to us right now, but I'll talk that through when we get there. You want to make sure that at each one of the joints, if there are any applied loads or any reactions that were either given to us in the problem or calculated in step number 2, we're going to include those at wherever that joint is located. We're also going to draw the forces along their lines or their members. So some of them are going to be horizontal, some of them are going to be vertical, but some are going to be at angles. So we're expecting that we're probably going to have to worry about some components, okay? We're going to use our equations of equilibrium. We have concurrent forces. Now, concurrent force system. What is a concurrent force system? What is something special about a concurrent force system? We talked about it in modules, I want to say module 2 and module 4. Do we remember? Concurrent force systems. Or no, module 2 and 3. We talked about resultants of concurrent force systems, and we talked about equilibrium of concurrent force systems. Concurrent force systems share a common point, or whether it is of application or of intersection, okay? That's where we had like the forces coming from that same point. Because we're going to be looking at individual joints, everything is coming and is being joined at the joint. It's a concurrent force system. So the two forces that, or the two equations of equilibrium that we look at when we start solving for the forces in the members are going to be the sum of the forces in the x equals 0 and sum of the forces in the y equals 0. Now, part D here, it says forces pointing towards our joint are going to be in compression, which means that any forces that are pulling away from the joint are going to be in tension, okay? And then I'll talk this through as well. When moving to a new joint, we want to make sure to keep the forces that were determined to be in tension or compression in that same orientation on the next joint. Okay, and again, that'll make more sense when we go through it. And then the last thing here is once we get through all of our joints, so we're going to work through the joints in our truss, however many there are, but when we get to that very last one, everything should equal 0. And then we know we did everything okay. All right. So, so one of the things that's really important as we work through these examples and any truss problem, take your time, create a nice big diagram. You're going to have to put a lot of labels in place. Don't make these dinky things. You guys, we're week 5 now. We only have 3 weeks left and I'm still seeing tiny, teeny little illustrations. Now make them big. Okay. Because you have to put your units in, you have to put your directions on, you have to put your labels on. Okay. And when we get into this, especially when we start looking at the positives and negatives and switching our directions, it's going to become crucial that you can follow along. Okay. So, so take your time on these. These are, the one missed positive or a negative in the wrong spot sets the whole problem off. So take your time. So we're going to be looking at example 6.2 on page 108. And again, that's out of the handout, the PDF that's in the learning plan for module 6. So I'm going to go to page 108. And page 108 at the very top is example 6.2. So I'm going to zoom in on the top here. And it says in figure 613A, which is this one right here, we have a simple plane truss. Okay. So as we look at our first page here, all of the assumptions that we were talking about on that first page are in play. Number one, the bars are going to be connected at their ends and they're going to serve as frictionless pins. Number two, all of the forces acting on the truss are applied at the joints only. We'll see that in this illustration. The members all lie in a single plane. So we're only worried about X and Y and we're in equilibrium. Okay, so those are the conditions, the assumptions that we're living by, if you would, in this example. So you'll notice here that we have a truss. It is supported at A and at D. A is a pin connection, and D, you'll notice, is a roller. There's little wheels underneath there. It has two applied loads, 4.5 at C going to the right and 13.5 kilonewtons going down at E. You'll notice that all of our dimensions are given here. We have 3 meters in between each one of the points along the horizontal, and then 4 meters high on the truss itself. So what I want you to do right now is to draw a free body diagram, but we're going to show all of the members, the points, the forces, but then replace the pin and the roller with the appropriate reactions that you would anticipate for each one of these spots, okay? Now, I am going to, oops, too many papers here. You can start here on page 2. I'm going to draw my free body diagram right here. I'm going to keep this up so that for those who might not have this handy, that you can reference the diagram. I'm going to put this here so that if you need to, I think it's a little bit more clear for you guys. And I'll create my free body diagram on the side here, and then we'll compare in about a minute. Now, again, I can't stress enough, make sure that you give yourself enough room for all of the dimensions, the labels, all that kind of stuff that we have on here. Don't forget your convention for the problem. So your free body diagram should look very similar to this. At A, you should have an AX and an AY. At D, you should have a vertical force. I have mine pointing up, both A and AY and DY pointing up. And then my X at A is going to the left because I have an X force going to the right already. And what we want to do next is determine AX, AY, and DY. Okay. Now, this part of the problem is module 5. We did a problem actually that looked almost identical to this that was a truss. Okay. So what we want to do here is we want to solve for AX, AY, and DY. Go ahead and do that. You should be able to move along using your 3 equations of equilibrium. Go ahead and get started, and then I'll kind of catch up with you guys. So as you're working, you should get dy equal to 11 kilonewtons. And I assume the direction going up, I end up with a positive value for my final answer. So that confirms that that was the correct direction. And then I got my AY 2.5 kilonewtons using the sum of the forces in the Y. And then my AX going to the left is 4.5 kilonewtons. Okay. So by getting that positive final answer, that confirms your direction. Or if you end up with a negative answer for one of your final answers, that just means, remember, you have to change the direction of that force. We never leave a negative as a final answer, ever, ever, ever. Any questions there? Did everybody get the same answers as me? Awesome. Awesome. Good, good, good. And that's module 5 stuff. Okay. Nothing really new here. We're just reapplying it to a new type of a problem. Okay. So now what we're going to do is we are going to go to the next page in our handout. Hold on. And we are going to continue on. So by looking at our process at the very top here, you're going to notice we did numbers 1 and 2. We drew our free body diagram as a whole, kept everything together, and then we determined the reactions at the supports of our whole truss. Now we're going to break down and we're going to look at each one of the individual joints. Now it says here where you know the most information. Now, as a new person looking at this, you're like, I don't know where I know the most information. I'm going to tell you, we know the most information at A or at D or at E or at C, because that's where we have some forces going on, okay? But the best place to really start is going to be at A. We're going to start there first, okay? So I'm going to walk you through the process of looking at joint A, and we're only going to look at joints. So again, this is called the method of joints, and we're going to be looking at each one of these joints separately. So on the next page, I'm going to label that I'm going to be looking at joint A, and I'm going to draw joint A. So I'm going to come down here, make sure that I have enough room. So this is going to be my point A or my joint A. I have a member going over to the right, which would be going to F. I've also got a member going up to B. So I'm going to draw those along those lines. Then the other forces that I have, and these are coming from the reactions at the supports, I'm going to draw AY at 2.5 kilonewtons going up, and AX at 4.5 kilonewtons going to the left. Okay. Now you don't even need to say AY is equal to, because we know we've established that there's a magnitude of the force there that's going up. And then we have the 4.5 kilonewtons going to the left. And this is point A. Now, along those two lines, what we want to do is we want to identify what those members are. So since this is point A, and if we look at our diagram, this horizontal line is going to lead to point F. So we're just simply going to call this AF or FA, whichever one you want to do. And then for the one that's going up and to the right, you'll notice that it's connecting A to B. So we're going to call that, AB. Okay. Now, additionally, we want to now put forces on here. Okay. Before I do that, let's identify my X and Y components. If I put my X's and Y's going right through the middle here, it's going to start to get super cluttered, especially when we need arrowheads to be added to everything. So instead of putting my X and Y components at the joint, they technically are going through there, but just for readability wise, I'm going to be putting my X and Y components a little bit off. You see the book do this as well. Now, to determine my directions, this is where before you actually start assuming, now you can, sometimes it's not obvious. We're going to come upon times when there are too many unknowns and it's going to be like, I just got to pick a direction. But if I have a few enough, I usually can kind of, figure some of this out. So if we look here, my opportunity for a Y, an unknown Y, is here at my Y, it would be my A, B, Y component, right? And if I have one other y force going up, to keep this in equilibrium, do you see why my ABY has to go down, right? Now, if my ABY is going down, the force along the member, which I need to identify, has to also go down, right? So to go down, that means it's going to be pointing at the actual joint. And because that's going down and to the right and to the left, then that means my X component, my ABX, has to go along with it. Kind of see how I made that work? Okay. Now, let's say you assign a direction and you have it going up and to the right. In the end, when you calculate your numbers, if you get a negative value for one of your numbers, that just means you assumed the wrong direction. And we're going to do just like we did in Module 5. We're just going to make it positive, switch the direction. That's why we use pencil, okay? So that you can erase it, no big deal. Chris?
Did you know to do the opposite of AY instead of AX? Because if you would have chosen X, it would have been the opposite thing that happened.
I chose it only because there was only one other opportunity for Y. So in this case, I have 2 opportunities for X's, right? That are unknown. In this case, I only have one unknown in the Y. That's why I chose to go Y's.
Oh.
Yeah. And as you get more experience, those things you'll start to like see that. Yeah. I'm kind of talking it through right now, and that's okay if you're like, why did she do that? You'll do some more of these and then you'll be onto it. You'll like kind of get it. Okay. But again, I don't want you to think that you have to at this point. Just assume a direction. All right. And make sure that, for instance, if I have my member going down and to the left, my X's and my Y's have to go along with that. If I have it going up and to the right, then they have to go up and to the right. So my X's and Y's have to go along with whatever the member is doing. All right. And then as we look here, you'll notice that, like Chris identified, look at my X right here is going to the left. I have a known going to the left. So I'm going to say that my AF is going to have to go to the right to balance this out, right? For equilibrium. So we'll see. Our math will tell us if we're making some good assumptions or not. Now, the other thing that's going on here is that our AX and our AY are components of a force that's at an angle, right? And that angle is right here. And it would also be this angle right there. That's the same angle. Okay. It's like that standard angle. So I can use a cosine with my X and a sine with my Y. All right. Let's go back to the first page here. When we created our free body diagram, we have our distances in here. So this is 4 meters high. This is 3 meters here. And if we use that same angle at A, theta, that's this angle right here. It's this angle here, that angle there, and that angle there, right? So what we want to do is we want to determine what is angle theta. So on here, I'm going to say tan theta is equal to, my side opposite is 4 meters divided by 3 meters. And if we do our trig, what do we get our angle theta to be? So if we take 4 divided by 3, and then take the arcsine or the arctan or the second function tan, whatever it is on your calculator, what do we get? How many degrees is that?
53.
Give me more. Yeah, I like that. So 53.13. When we're doing angles, I would hold 1 or 2 decimal places, okay? Just because we're going to be then using the decimal equivalent of the sine and the cosine, and we want to have a little bit more so that we can be more accurate. So that's that angle. And that also is this angle right here, okay? So let's figure out what our X component, our X and Y components are in terms of their hypotenuse. So up here, I'm going to do the components, okay? And I know that ABX is going to be equal to, it's that same angle right there. It's going to be the cosine of 53.13 degrees times AB, right? It's hypotenuse. So the decimal equivalent then of the cosine of 53.13 is what? Is it 0.6? Okay, 0.6 times AB. Okay. We'll be using that. Remember, we always want to know what is the force, the magnitude of the force in the member. The member is the AB, not the ABX or the ABY, right? Let's do the same thing for the Y. ABY is going to be equal to the sine of 53.13 times AB. So 53.13, do the sine of that, you should get 0.8, right? Times AB. Now, because of the position of this and because of the triangles and the way that they're at, we'll check it at each step. What we're going to find, anytime we have an X component, it's going to be 0.8 times whatever its hypotenuse is or whatever the member is. And then when we see a Y, we're going to see it as 0.8 times whatever that hypotenuse is. Okay. All right. Now we're ready to start looking at these individual forces and figuring out what we know and what we don't know. So let's start by using our first equation of equilibrium. Let's sum our forces in the Y direction equal to 0. I'm only choosing Y first instead of X because I've only got one unknown in the Y. Okay, so I have a better chance of solving for something than having too many unknowns. So as we look here, summing the forces in the Y, I've got a positive 2.5 kilonewtons, right? I've got a negative now ABY, but instead of putting ABY, I'm going to put 0.8 times AB, okay? 0.8 times AB. And I'm just going to, you don't have to do this, but I just want to identify it that the 0.8 times AB is my ABY. And it's going down, that's why it's negative. Those are the only two forces in the Y direction. I set that equal to 0. So my only unknown here is the AB. So I can move this over to the other side. Negative 0.8 times AB is equal to negative 2.5 kilonewtons. Both of those negatives become positive. I'm going to divide by 0.8. What do you get for AB? Yep, 3.125 kilonewtons. Now, we're not done. We found the magnitude in the member. We need to now assign, is it positive, or I'm sorry, is it in tension or is it in compression? Okay, so we need to look. If we go up here, you'll notice that AB is pointing towards or pushing on the joint. If we go back to our process, it says here, forces that are pointing towards the joint are going to be in compression. Those that are pulling away are in tension. Ours is pointing towards. That means that this is in compression. To show compression, I just put in parentheses a C in back of the value. So you need magnitude for me, and you need to tell me, is it in tension or compression? And when I look up here, I want to see that AB is labeled and pushing on the point. Okay. This is an answer, so I'm going to put a box around it. All right, so I know what AB is. I know AB is 3.12, see, make that so we can read it, 125 kilonewtons, okay? Now I want to sum my forces in the X direction because I want to figure out AF is my next unknown, right? AF. So I fit it here. I'm going to try to fit it here on the right-hand side. I'm going to sum my forces in the Y direction equal to, I'm sorry, we did Y, we're going to do X. So if I'm going to sum my forces in the X, I've got a negative 4.5 kilonewtons. I've got a negative, now this is ABX, 0.6 times, I know what AB is. I know it's 3.125, right? So I'm going to multiply it by 3.125 kilonewtons. This is ABX. And it's pointing to the left, so it's negative. And then I've got AF going to the right, so plus AF. AF is my only unknown. I set that equal to 0. Go ahead and solve for AF. So when you multiply 0.6 times 3.125 plus a negative 4.5, you should have gotten a negative 6.375 on the left-hand side, right? And then you're going to move it to the other side, it becomes positive. So we have a positive value, 6.375 kilonewtons, meaning that the direction that we assigned AF is correct. Okay, we don't have to do any, moving around. But now that we have its magnitude of 6.375 kilonewtons, we need to determine, before we move on, is this in tension or in compression? Our joint is A, it's pulling away from the joint. You need to look back. Is this tension or compression? Tension, yep. So we're going to put in parentheses a T in back of it. And then we're going to put a box around that. Each one of these members is a final answer, something we're looking for in these problems. Okay. Questions? All right, we've got one joint done. One joint done. So we did joint A. Now what we want to do is we want to go to an adjoining joint. Okay, so the next joint that we would go to would either be to B or to F. We would not skip over and do C, E, or D. Okay, we go in order here. So do we have a preference? Do we want to do B or F? Let's do B. Let's do B. So I'm going to draw B down below here. Okay, so I'm going to go back over here. I'm going to start with B. I'm going to draw the lines in the directions, these three lines coming from B. And then we're going to label each one according to what it's connected to. So this is going to be joint B. I'm going to start with P like here-ish. Okay. Now, AB, we already did. I'll talk about that. So I would put it in place, identify its X and Y's, but don't put an arrowhead on it because I'll share with you how we determine which way it's going to go. Okay, so once we have our lines coming from each one of the directions to B, so we've got B going over to C, B going down to F, those are, horizontal and vertical, but then we have the one coming in at an angle coming from AB. We already calculated AB, and since AB is on a line connecting these two, whatever we determined the force to be when we determined it at A, it's going to be the very same force at B. And what we determined it to be in either tension or compression is going to be the same tension or compression on B. So we want to look. We know that we already calculated AB. We're going to go back up to joint A. AB is 3.125. That's its magnitude. And it's in compression on A. So it was pointing towards A. That means that it has to be in compression at B. So it is going to point towards B. Okay? Has to. So if it's a compression on one, it's in the compression on the other. And which means that when you go from one to the next, we like switch directions of the forces. Now, we know that AB is 3.125 kilonewtons, right? And if this is going up and to the right, ABX has to go to the right. ABY has to go up. Now, because we know the magnitude of AB, we can calculate the X and Y components directly, right? So we know that AX is 0.6 times AB, and we know ABY is 0.8 times AB. So I'm going to put those numbers in each direction here. So I'm going to take 3.125, multiply it by 0.6, and that is going to be my X component, 1.875 kilonewtons. And then my Y component is going to be 3.125 times 0.8, which is going to be 2.5 kilonewtons. Okay. And those are definitively known. You have, don't draw this going down and to the left. Remember, if it's in compression on one joint, it has to be in compression on the one that it's connected to as well. So it's got to like switch directions. And so it has to point at B here as well. That was a compression member. It's pressing on each. Now, as we look at putting arrows on BC and BF, okay? Now that we know the direction of AB and the direction of its components, now it becomes a little bit more clear the way our BF and our BC are going to go. So since I have 2.5 going up on the Y component at AB, that means that BF has to come down, right? Has to. And for BC, since we have the component of AB going to the right, BC has to go to the left. Okay. So always start with the known stuff first, and then put your arrowheads in after. So now when we sum our forces in the X and Y, we should get positive numbers because these directions look good. So let's go ahead and do that. We're going to sum our forces in the X direction. And I've got a positive 1.875 kilonewtons minus BC for that is equal to 0. Those are the only two forces in the X. Now I'm going to move my 1.875 to the other side. Negative BC is equal to negative 1.875 kilonewtons. They both become positive. You could move the BC to the other side. I just like having my variable on the left. So either way. Now, before I move away from BC, I need to identify, is it in tension or compression? Tell me. Oh, I've got somebody. I hope I didn't. As we do the joints, thank you. Do we also need the conventions? No. Oh, good question, Aaliyah. We started the convention at the start of the problem. Okay, I'm sorry. It's been 5 minutes. You had it up there. I didn't notice it. But on the original free body diagram right here, this is like the start of the problem. You just have to put it once right there. You don't have to put it on each one of the joints. Thank you for asking that. Thank you for asking that. Okay. So getting back to BC, tension or compression? Compression. Why is it compression? You're correct. It's pointing towards the point. It's pressing on the joint. Exactly. So this is going to be in compression, and we're going to put a box around. So I want boxes around these answers because that tells me that you're answering what is the magnitude of the force in the member. And this member is BC. Awesome. So now we're going to do BF. Sum the forces in the Y direction equal to 0. We've got a positive 2.5 kilonewtons. A minus BF is equal to 0. Those are the only two that are going in the Y direction. So now I'm going to have negative BF. Oopsie. BF equals negative 2.5 kilonewtons. Both become positive. So my final answer is positive. I assumed the correct direction. And is BF tension or compression? Tension. It's pulling away from the joint. Tension. Box around magnitude and tension compression. Awesome. Questions so far? Yeah. Reapplication of stuff that we've done already, right? Just in a you know, a new form, if you would. All right. So going back to our overall free body diagram, we've done A, we've done B. Where do we want to go next? Do we want to go to F or do we want to go to C? Let's do C. I agree. Let's do C. Let's see what happens at C. So I had this page right here. This was page 3. I'm going to turn mine over. You might still have room. Everybody draws smaller than I do. And what we're going to do is we're going to start with point C here, and we're going to draw all the lines coming from C. All the lines coming from C. Okay. Start kind of in the middle. Joint C. I know I'm gonna run out of room on my handout, but that's okay. Got it. Straight down. We got one here too. This is a busy joint. Don't you think? See. Don't forget the 4.5 kilonewtons. It's going to the right. Now I have my lines on here, but I do know a little bit more than this. I know what BC is, right? Because I just did joint B and I calculated BC. So I've got to go back to joint B to find out its magnitude and if it's compression or tension. So the very last one that I did, here's BC. It's pointing towards, so it's going to be in compression. And BC is 1.875 kilonewtons. Okay, compression. So since it's in compression on B, it has to be in compression on C. So that means I'm going to point to the right. Okay. And what was that number? 1.875. Okay. 1.875 kilonewtons going to the right, pointing on C in compression. Okay. Now, those are the only two forces I know. So I've got to make some assumptions about my next ones, right? So, so as we look here, I've got two going to the right. So there's a good chance that I'm going to have some of my X's going to the left or to the right. So what I can do is, since my X opportunities are here and here, all right, I'm going to show, for instance, my CD. I'm going to show that going up and to the right. Okay. Which means that my X component has to go, I'm sorry, up and to the left. Has to go to the left. So this is going to be CDX. This is going to be CDY.
So vertical. Force the 13.5.
Yeah. No, I don't have it at CE. There's no force coming down at but I'm not to E yet. E is down here, physically down here. This is just a line connecting the two. So that's on the joint that's at E. We're at C right now.
No, I think that you have to find a C, E, get that actual.
I haven't gotten there yet. Yeah, we have to put an arrow on. So we assume an arrow. So this one is going over to the left. Which direction do we want to put? I want to put my CF here now. Which way direction do we want to put CF? Up and to the right, or up and to the right, or down and to the left? Down and to the left. Sure, let's do it. Now, again, these I'm not sure of. They could, I'm not exactly sure what these are. So I'm going to assume a direction and we'll go through the process and we'll see if we were okay. Okay. CFX, CFY. And then I do have my CE yet. So which way do I want to show that one? Going up or down? Assume a direction. Any ideas? You want to show it going down? Okay, we'll show it going down. And then as we work our numbers, we're going to find out if we were correct or not. Okay. So again, some of them are obvious, some of them aren't. Okay. I don't feel this one's super obvious. So we'll see. So now what we get to do is we need to sum our forces in the X and Y and see how far we can get. So as we look here, is there any direction where we feel like we could solve for something, like there's only one unknown, X or Y? In the X, I've got 2 unknowns. In the y, I have 3 unknowns. Okay. No big deal. We'll write our equations and we'll just get as far as we can. Now, the other thing we need to recognize here is we have some x and y components, right? So we have that theta would be here, which will be this angle there. And we also have that same theta on this side, which is that one there. So for our x's, remember, we're going to use 0.6 times whatever the hypotenuse is. And for our y's, it's going to be 0.8. So we would say that our CFX is going to be equal to 0.6 times CF. You do not have to write that work out again because it's the same as what it was when we did it on our first joint. CFY is going to be 0.8 times CF. CDX is going to be 0.6 times CD. And CDY is going to be 0.8 times CD. Any questions on that? Make sure you show, because you're going to see this come up because they're triangles, okay? And they're the same, width and height. So these numbers end up, being the same angles throughout the truss. That's why we can do that. All right, now we're ready to sum our forces in the x and sum our forces in the y. So I'm going to sum our forces in the x direction equal to 0. Right now we have a positive 1.875 kilonewtons going to the right. We have a positive 4.5 kilonewtons going to the right. We have a negative, now it's CFX. So instead of writing CFX, I'm going to write 0.6 times CF. This was my CFX going to the left, so it has a negative in front of it. Then I also have a negative CDX, which is going to be 0.6 times CD, which is my CDX component. Now, again, these are all going through the point, but I have them offset. As you can imagine, there would be just a ton of lines and arrowheads trying to go on the same spot. Set this equal to 0. Now, what I'm going to do is I'm going to combine what I can on this side. I can't combine these, and we're simply going to say 1.875, 4.5 plus. So this is going to be 6.375 kilonewtons minus 0.6 times CF minus 0.6 times CD equal to 0. And that's as far as we can go. There's 2 unknowns, right? But I can do my sum of my forces in the y. So let's try that. I'm going to leave some space here because I know I'm going to probably come back. I know I'm going to come back. I'm going to do a sum of forces in the y equals 0. So here, I've got a negative CFY. So I'm going to write 0.8 CF. So negative 0.8 CF. Okay, that's my CFY. I'm going to have a minus CE. And I'm going to have a positive CDY, which is 0.8 times CD. Okay. Equal to 0. And these I'm going to leave there. There's no use combining anything because nothing can combine. And I'm just going to leave those as is on the left-hand side, set equal to 0. That's as far as I can go here. I don't have 2 equations with the same 2 unknowns, so that's as far as I can go. So all that means is I have too many unknowns at this joint. I got to pick something else. That's it. No big deal because we can always come back to it. We've got it set up. So we did A, we did B, we tried C. Where do we want to go this time? Yeah, oh, yeah.
We can't use the third equation. We're doing,
No, we can't. Because if we sum our moments around C, we don't have any offset forces to cause a rotation. Everything's going through. Yeah, no, good question. I'm glad you asked that. We can when we do our initial here because we've got offset distances, right? But now we're in that concurrent force system. And unfortunately, we only have our 2 equations of equilibrium because of that. Thank you. I'm sure somebody else was thinking that same thing. I'm glad you asked that, Chris. That's why we're not using the sum of the moments. All right, so joints, where do we want to go? So we did A, we did B, we tried C. Well, we're going to go back to it, no worries. Where should we go now? F, yes, F. F, we did B, so we know a little bit of something there, and we did A. So F would be a good one to try next, okay? I need to start a new piece of paper. So I'm gonna start F on my next piece. So this is gonna be joint F, joint F. So F, let me start here. I'm gonna draw a horizontal line. One going over to A, one going over to E, one going up to B, and then we also have the one going up to C, right? This is point F. Now, F doesn't have any forces coming from it. Oopsie, let me go back to here. So F just has the connection to each one of the joints. Okay. So going to the right is AF. Going up is going to be BF. Going up over here is going to be CF. Whether you put CF or FC does not matter. And then FE. Now, the places we are going to be able to know is we're going to go back to B and we're going to go back to A. So I'm going to start by going back to A. Okay. Here's my joint A. You'll notice that here's my AF. It is pulling away from the joint. It's in tension and its magnitude is 6.375. Okay. So since it's in tension pulling away from A, it has to be in tension pulling away from F. Okay. And its magnitude 6.375 kilonewtons. Okay. B. Okay. I'm going to go up to joint B. Joint B had BF. BF was pulling away in tension off of B, and it was 2.5. So it has to be in tension off of F. So it's going to pull away from F. And this is equal to 2.5 kilonewtons. Now, as we look at CF here, we tried CF on C, but remember we couldn't solve for it. So we weren't able to even determine if the direction that we assumed there was right or not, right? So we're not even going to worry about what we did over on C. We'll devise a plan based on what we have here. So we have one force in the Y direction and one opportunity for a Y here, right? CF. It's going to have a Y and an X. As we look here, because there's only one other Y force, which direction should CFY go in, up or down? Should go down. If this is my only other force in the Y, this one has to go down, has to. So CFY has to go down. If CFY has to go down, what is the direction of CF? Down and to the left or up and to the right? Down and to the left, because the Y is down, has to. So that means that my CFX has to go to the left. Okay. Sometimes it's not obvious, like C was not obvious. There was that extra unknown in there. And then it is kind of like, oh, I don't know which way it's going to go. Okay. Don't worry about C just yet. We'll deal with that in a little bit. But now we've got to find a direction for FE. If we have two X's going to the left, which way does FE go? To the right. Yep. To the right. Good. Good, good, good. Now, CFY is going to be equal to, I'm sorry, let's do our X first. CFX is going to be equal to 0.6 times CF. CFY is going to be 0.8 times CF. Again, here's our theta. Here's our theta. Does everybody understand why that is? Okay, because the cosine of 60 is 0.5. So cosine of 60, I'm sorry. Oh, no, it was the 53. We're gonna have 60 on our next one. That's why I had statics just earlier and I did this very same lecture. So it's the cosine of 53.13 is 0.6 and the sine of 53.13 is 0.8. Okay, now what do we get to do? What's our next step? Sum the forces in the X and Y equal to 0 to determine our CF and our FE, okay? Let's start with sum of the forces in the X equals 0. So I've got a negative 6.75, negative 6.375, is that right? Yeah. A positive FE and a minus not CFX, sorry, 0.6 times CF, right? Is equal to 0. Now I do have two unknowns here. So I'm gonna just kind of let that sit a little bit. I'm gonna do my Y next. So I'm gonna leave a little bit of room here. Sum my forces in the Y equals 0. I've got a positive 2.5 kilonewtons, and I've got a minus CFY or 0.8 times CF. Equal to 0. So now we're going to move the 2.5 on the other side. It becomes negative. I've got two negatives, both become positive. Divide both sides by 0.8. My CF (3.125 kilonewtons. Does that sound right? Before I call this or put a box around it, I need to determine, is it tension or compression? So I look back up here, I ended up with a positive value. So the direction I assumed up here is correct. It's pointing towards the joint. So this is in compression. Box around the final answer. Okay. Now I can use that very same thing and I can plug it in right here. Okay, so this is going to be negative 6.375 kilonewtons plus FE minus 0.6 times 3.125 kilonewtons equal to 0. Combine what you can here and FE and then move to the other side. FE is going to be equal to you should get a negative 8.25 on this side. And when you put it to the other side, it becomes positive. So FE is going to be 8.25 kilonewtons. Now, before we put a box around it, is it tension or compression? Tension, pulling away, right? FE is pulling away from F. It's in tension. There we go. Everybody got this one? I check not only do you have the right tension or compression, but I look at your free body diagram to be sure that you are, that you have your arrows going in the right directions. I encourage you. I'm not going to require it, but I encourage you to use straight edges on this stuff, okay? Because it's going to be so much easier for you to see these things. And to also kind of offset these X and Y so that you don't have like all of these arrows coming together at the joint. Because then it's going to be really hard to decipher. It's going to be like a black blob in the middle otherwise. Okay, so now that we know CF, we can take that back to joint C, right? Now, we know CF to be 3.125 in compression, okay? So we're going to go back to our C, okay? Joint C, we had to stop. Now, let's look at our free body diagram first. When we drew it originally, we drew it in tension. It's not in tension, is it? We confirmed that it is in compression. So this is why we use pencil. We're gonna erase the arrowheads on all of our CFs. And we're gonna point towards the joint with CF, which means that our CX is gonna go to the right. And our CY is gonna go up. Okay? You have to do that work first, right? You have to get that right first. Now, once you have the CF pointing towards C, the CX going to the right, the CY going up, now we have to go back into our equations and we have to update the signs. So CFX, it's right here. It is now pointing to the right. We need, oops, I can just make that positive. This needs to be positive. Positive. Okay. And I have to go down here in the next line and make it positive here as well. If you did 2 lines, make sure you make them both positive. Now I'm going to go to my CY because that changed direction as well. Go down to the Y equation. That CF, the 0.8 times CF was my Y. That needs to be positive out front. Okay. Now we can go in and substitute our value of 3.125 for CF. Okay. So this is going to be 6.375 kilonewtons plus 0.6 times 3.125 kilonewtons minus 0.6 times CD is equal to 0. Notice that we only have one unknown here now. Okay, one unknown here. So we can solve for CD. Go ahead and do that. Combine these two, put them the other side. So you should get 8.25 combined over here, negative or positive. It goes to the other side, it becomes negative. 2 negatives become positive. So 0.6 CD is equal to 8.25. Divide both sides by 0.6. And we get CD equal to 13.75 kilonewtons. Okay. Now, before we go to the next one, we need to determine is CD in compression or tension. Because we ended with a positive final answer, the direction we assumed going up and to the left is correct. We don't have to change anything direction-wise. And since it's going up and to the left and it's pointing at or towards our joint, this is going to be in compression. And then we can put our box around our answer. And now that we know CD, we can substitute it into there. We know CF to be 3.125. So our only unknown down here is CE. Go ahead and solve for CE. So once you combine on the left-hand side, you're going to get a positive 13.5. You push it to the other side, it becomes negative. So negative CE is equal to a negative 13.5. They both become positive. they both become positive. CE is pulling away, tension or compression? Tension, yep. And we put a box around that answer. So good. All right. So now we did A, B, F, C. Where do we go next? E. Okay. D will be our last one. E. So go ahead and draw free body diagram of joint E. Make sure you include the 13.5. Make sure you go back to C and F, okay, to get the magnitudes and the directions. Won't be able to fit it, so I'll do it up here. Joint E. So E is connected to C. So along member CE, we've got to go back to joint C. We just did that one. Joint C had CE in tension at 13.5. Okay. So if it's in tension on C, it has to be in tension on E. So it's pulling away. So it's going to go up. And its magnitude is 13.5 kilonewtons, which is very good news. Because as we look here, if we would sum our forces in the X, what would we get? 0, right? It's in equilibrium. If you would get to a joint like this and you have an external force and the only other force here is its value and your force is something else, you did something wrong along the way. Okay, unfortunately. Then you have to kind of go back and kind of see. But this is good news. This is good news. Now, as we look here, we go back to point F, is on my other side here. FE is in tension, pulling away. Its magnitude is 8.25. So that means that it's going to be in tension, pulling away from E, 8.25. Now, my only unknown then is the member going over to point D. So we're going to call that ED. And my only unknown is ED. So I'm going to sum my forces in the X direction equal to 0. And I've got a negative 8.25 kilonewtons plus ED is equal to 0. ED is going to be equal to 8.25 kilonewton, positive value. So the direction is correct. And it's pulling away from E, so it's in tension. You don't need to do a sum of the forces in the Y because there's nothing to solve for in the Y, and we can see that they balance out. Okay. All right. One last joint. And this is when we know it all worked out. It all worked out. So we're going to do joint D. Go ahead and draw your joint D, and don't forget to put the 11 kilonewtons in there. Okay. as we look here, I'm gonna go back to my previous joint at E. ED was in tension 8.25, sorry, oh, I put the wrong number there. 8.25 kilonewtons. Looking at the wrong one. Okay, 8.25 kilonewtons, and it's in tension. So if it's in tension at E, it has to be in tension at D. So it's going to be pulling away, going to the left. CD, we have to go back to joint C. CD was in compression, pushing on C, so it has to be in compression on D. So it's going to be going down and to the right. So that means that our Y component is going to go down and our X component is going to go to the right. Okay, so CDY and CDX. Okay, now we're going to have to calculate the magnitudes of these to make sure that they balance out with the numbers going in the opposite directions. Directions right now look great. I've only got one Y or two Ys. I've got one going down and one going up. I've only got two X's, one going to the right, one going to the left. So my hope is CDY is going to equal 11 and CDX is going to be equal to 8.25. So to do that, I know that all of my Y components are multiplied by what? 0.8 or 0.6? 0.8, right. So I'm going to take 13.75 and multiply it by 0.8. Oh, look at that. 11 kilonewtons. Then I'm going to take 13.75 and multiply by 0.6. And that is 8.25 kilonewtons as well. And it's going to the right. So if I sum my forces in the X direction, they all equal 0. And if I sum my forces in the Y direction, they all equal 0. And that makes for a very happy person at the end. If you don't get these equaling to 0 at the end, then somewhere along the way, it's going to be a negative or a positive sign that wasn't carried correctly. It always is. Always is. And then you got to try to figure it out. Now, you're going to notice at the end of this, or I should say, are there any questions here? Does that make sense to everybody? Now, in the olden days, when I got to do this, we had to wait till the end to know if we did it right or not. Okay. We just did. One thing that you'll notice as you go through though, did you notice that we kind of started seeing similar numbers as we went along? Like the same 3.12 came up. That's a good sign that you're on the right track. If you start getting like weird numbers and nothing is repeating ever, then you might have a little suspicion that something might be off. Okay. But at the end is when you know. But luckily, we have MD solids that can help us to determine that. Now, in this case, we have the example that we could follow along with and check our answers, but you're going to have application problems that you don't have the answers for, and I'm not going to give them to you because I want you to run MD solids to see, you know, how it looks. So I am just going to do a demonstration. My intent, please do not worry about downloading this at this moment. All I want to do is show you what it looks like right now. The next time that we have class at the beginning, I'm gonna have you guys kind of try it out and make sure you know how to use it. Or even in between, after you see this demonstration, you're gonna be like, I know how to use it. It's really easy. Here's MD solids. Once you come in here, when you do it the first time, it's gonna ask you for a username. Just put your initials in and it's gonna ask you for a registration code. That's that D number. And it's also gonna be on the page where you do the download. So I'm gonna click on trusses because that's the area that I'm going into. And I'm going to start a new truss. I'm going to start a new truss. So I'm going to click on here. Now, what it's going to ask me for is define my truss grid. This is going to be just the little endpoints that I'm going to have. So if I go back underneath, oops, I think I closed this out. If I go back underneath here, it's going to want to know what is my horizontal spacing. My horizontal spacing is 3 meters. Okay, so it's 3 meters, 3. And then the number of spaces. If I go back underneath, there's 1, 2, 3, all right? So I'm going to change this from 4 to 3. So 3 is my number in between, and there's 3 spaces. Then vertically, my number is 4 meters, but just 4 for units, and there's only 1 value up. If you had multiples, you would add those in. So I'm going to hit OK. And now it just creates a grid for me. From here, over on the left-hand side, you're going to have create. And then I'm going to create my members. Those are the members in between the joints. So I'm going to start in this lower left-hand corner. I'm going to left click, drag, and release when I get to a corner. It's going to snap. Then I'm going to left click, release, and I'm going to put it in the configuration that we see. Do not do a continuous all the way to the end. These have to be joints at each one of the different members, okay? So they're individual pieces. This one goes from here and up, over, down, and over here and over. Now, let's say I did one and it's not in the right orientation. You can hit erase, keep member here, and all you have to do is go over the top of it and it erases it. And then you can go back to create, left click, and then go up where it needs to go. That's how you can erase something. It's not a sophisticated CAD system, okay? So it's kind of click, drag, and release when you get to the point. Now that was my members. I'm going to now put my supports in place. I'm going to click on my supports. I'm going to do the, it always does the roller first. So I'm just going to click down. It's going to show me a roller. I want my roller at D. I want a pin at A. So I'm going to first click down, and then I'm going to click up, or no, click to the left. And then it's going to change it to a pin. It'll always do roller first and then a pin. Okay. So I've got my pin at A. I've got my roller at D. Now I just need to add my loads. Okay. Need to add my loads. So I'm going to go over to my 13.5 going straight down. Notice that depending on which way I go here, it's going to drag. So I'm still depressing and I'm holding, and I'm just going to release when it goes in that orientation. The magnitude is going to be 13.5. Then I'm doing the same thing up here. Go to the right, 4.5, enter. So now that I have all my information in here, and if I wanted to erase, I could do that very same thing. Hit erase, go over the top of it, and it would go away, and then I can re-put it back in. Now, once I have everything the way it's supposed to be here, I hit compute. Look at that. And there are all my values with C or T in back of them. Now, units aren't in here. We're not really concerned with units. I mean, I know that they're all kilonewtons, but we didn't have to enter that in. It's just generic values, okay? The C and the T's represent your tension or compressions. And if you compare this to the values that we got, they're exactly the same, okay? Also shows us our reactions at our supports here. So when you do your homework, I'm going to have, I think, one problem that you guys are going to do that you're going to work it manually, and then you're going to do the MD solids for me, okay? What I would do if I were you, because I'm not giving you the answers, you're going to run MD solids first. Now you've got your answers, and then you're going to work the problem manually so that when you do A, you can be sure that you get the right values for up to E or whatever. They did their numbers or their letters a little different. I don't believe you can control that. They just randomly do that, but you would go up to your value and compare. Okay. So MD solids is here. And then you're going to have two or three problems, I forget, that I just have you do the MD solids, practice using it. Okay. And you don't have to do the manual calculations. So one with manual, the first one, both manual and MD solids, run MD solids first. And then the second and third, you're going to be doing just the MD solids. Okay. So, so between now and the next time we meet, get MD solids downloaded, maybe even play around with it, see if you can kind of figure it out. But the next time, the first thing I'm going to ask are, let's go over a couple of these MD solids ones and make sure that we've got a good handle on that. Okay. So that problem was long. We're going to take a break. We're going to take a nice 15-minute break. So what I'm going to do is I'm going to stop recording now.